Okay, and so before we jump into this part 3, I just want to give you some clinical examples of ways that we can generate image contrast. So another thing that we talked about last time was this gadolinium chelation process, where we inject this gadolinium chelate into typically intravenously, and it shortens the T1 of arterial blood, which means that we can actually use some of our T1 weighted imaging strategies to get images of just the blood vessels. And so this is an example of a cranial contrast enhanced MR angiogram. So typically the way this is done, you acquire one image without contrast, you inject contrast, you acquire another image with the exact same slice location and the exact same parameters, and you do a subtraction between the two, and the difference gives you this, these nice angiograms. Another thing that we can do with this T1 weighted imaging is something called arterial spin labeling. So last time we talked about this idea of inversion recovery. So if we apply 180-degree pulse to the magnetization, we know that it's going to follow this recovery curve. So typically what we do in arterial spin labeling is we label the blood downstream from the tissue of interest and allow that blood to then flow in and exchange with the unlabeled blood in the tissue of interest and collect an image. Then we collect an image with the exact same parameters without applying that inversion, and the difference is going to be directly proportional to perfusion. Here's an example of using proton density weighted imaging in brain tumors. We know that gray matter, white matter, CSF in a healthy subject are going to have specific properties. When we start talking about tumors, they're going to have drastically different properties, typically presented as, in this case, proton density. So you can see this large tumor here on this proton density weighted image. So remember, this is a long TR and a short TE, so that we've mitigated any T1 relaxation effects or T2 relaxation effects. And so we can see here the drastic difference in this proton density weighted image in brain tumors. We can also apply multiple different types of imaging to the same disease state. This is an example of multiple sclerosis. So here we have a proton density weighted image, and you can see some of the lesions that appear bright on this proton density weighted image. This is a T2 weighted image. And this is a gadolinium enhanced T1 image. And so you can see the lesions across all three of these different modalities. And these bright spots here in the gadolinium enhancement indicate areas where we have breakdown of the blood-brain barrier. So not just areas of demyelination, but also actual breakdown of the blood-brain barrier. Okay, so that brings us to part 3, gradients and echoes. And just to remind you of our color scheme. So remember, blue is our B0 field, green is our RF or B1 field, red is our spins unless otherwise indicated on the slide. And so we've got this pink magenta E color that indicate gradients. And so the image on the left here is just an example diagram of what gradient coils actually look like. So these are another set of coils that fit inside of our magnet. So we already talked about how we create this B0. We talked about how we create B1 with the RF coil. And so these gradient coils actually fit also inside the machine itself. So you don't actually see these gradients unless you've got a big problem. Because you've actually had to take apart your magnet. But more often than not, the B1, the gradients, and the B0 are completely hidden from you inside the machinery. Okay? And so if you remember our Larmor equation way back from part 1, so we talked about the fact that this precessional frequency is directly proportional to the magnetic field that we impart to the spins. So we already talked about B0, we talked about B1. Well, the idea with gradients is that now we take it a step further and we make the magnetic field experienced by the spins a function of not only time, but also X, Y, and Z. Okay? And the way we do that is by applying a gradient. Okay, so if you look, let's pretend that we're applying a positive linear gradient in the z direction. So what that actually means is that if you were to map what the spins we're experiencing along the z direction, you would see something like this. So more negative if your z position is lower, and if your z position is higher, you would be experiencing a larger BZ. Okay, so this is just changing the magnetic field as a function of z. Okay, so what that would look like, or just a graphical representation of this, some of you may have seen pulse sequence diagrams that have these gradient waveforms on them. So this is just typically what it looks like. So you would have, in this case we're talking about gradient in the z direction. It would just be some positive value that looks like this, and so it looks something like this. Just a linear shift in the z component of the magnetization along the z direction. Okay, if we increase the amplitude of GZ, then we're going to increase the slope of this this ramp that we're showing here. If we make it negative, then it just flips sign. Okay. Now, just to give you some perspective of the amplitudes of the Z shift that we're imparting to this large sample that we're trying to collect data from. So if you typically think about the maximum allowed imaging field of view in most clinical scanners is about on the order of 50 centimeters. The maximum gradient that many magnets are able to crank out, so the amplitude of this GZ value is about 40 millitesla per meter. And so what that means is that across this field of view, we're talking about a maximum change of plus 10 millitesla at the farthest edge of this field of view and minus 10 millitesla here. And so we're talking 10 millitesla as compared to 3 Tesla or 7 Tesla or 1.5 Tesla. So it's a very minor change in that magnetic field. And just to put that in perspective, so I showed you this graph a little bit ago where we looked at the GZ or GZ as a function of Z. It looks something like this if we're applying a positive GZ. Well, remember, it's a very small magnitude compared to our main B0, so it really looks something more like this. Okay? And now, what we can do is, we know that the protons are always going to be precessing with that known Larmor frequency that is directly proportional to the magnetic field that it's experiencing. And so if you think about in the absence of any gradient, we're going to have protons at this Z location, and this Z location. They're always going to be precessing with the same frequency. However, if we apply this positive Z gradient that looks something, so if we think about this in terms of frequency as a function of Z position, when we apply this GZ gradient, we get, in this case it's positive. So what that means is that protons that are in a positive position compared to the very center of our magnet, they're going to be precessing with a slightly faster frequency. This is just simple plug-in equation 1. We know that the magnetic field at these positions is higher than at the middle and over here. So what it means is that right in the middle, we're still precessing with the same BZ, omega 0. Over here, we're precessing slightly faster. Over here, we're precessing slightly slower. Now, one of the best examples of how we use this on a day-to-day basis is slice selection. And so if you think about the brain being a stack of these 2D slices, if we know that we want to image this particular slice, then what we do is we apply our GZ gradient like this, and we know that the frequency is going to be given by this. And so all we have to do is, if we know that we want this particular Z slice, we know now exactly what frequency we need to apply our B1 field at. okay? And so that's just the simplest example of ways that we actually use gradients to spatially encode our MR signal, okay? And so that would look something like this. So if we have a GZ turned on during our RF application, then we know that we're exciting a specific slice in the Z direction, okay? All right. So we can also apply gradients in X or Y. It doesn't just have to be Z. Now, this brings up one of the biggest misconceptions in MR. So we've already talked about a few of the misconceptions back during part 1 and part 2. This is another pretty significant one. So if we're applying a gradient along the X direction, it looks something like this. We are not changing the X component of the B field as a function of X. That is wrong. What we're actually doing is we're changing the Z component of the main magnetic field as a function of X. This is a huge misconception. We're not applying a magnetic field in the X direction when we're applying the gradient. What we're doing is we're changing the Z component as a function of X. Remember, we apply our RF field in the XY plane to get the magnetization to tip away from the equilibrium state along the Z direction. So it's important to realize that when we're talking about applying gradients in the X direction, this is actually what we mean. So we're changing the magnetic field as along the Z direction as a function of X, okay? And so we can do, so if we look at what this looks like. So again, we have our main B0 field that looks something like this, and we're applying this GX along the X direction. So remember, we're changing the Z component. So what that means is that in the absence of any gradient in any direction, we have normal precession along the X direction at the known Larmor frequency, okay? And so we know that all of these spins are now precessing with the same frequency. When we apply that gradient in the X direction, in this case it's a positive gradient. So what that means is that compared to the center of the magnet, protons that are in a higher X position are going to be precessing faster than protons that have a lower X position that are going to be precessing slower, okay? Now, I want to point, the other thing I want to point out here is that they're all still precessing in the positive direction, I guess, if you want to think about it that way. That it's not that this one's actually precessing in the opposite direction. It's just that it's not precessing at quite as fast of a frequency, okay? So by applying this gradient, what we're changing is the amount of B field that the spins are experiencing in their particular location along the Z direction. So gradients are, yes, technically gradients are another type of magnetic field, but what you can think about them as is either a slight bump or a slight pullback of the main B0 field. So we already talked about how low the amplitude is. So what you can think about it is that in this particular quadrant of the body, when you're actually in the magnet and applying a particular set of gradients, you know you're going to have a specific frequency in that location. Okay? Okay, and so we can do this exact same thing by applying a gradient along the Y. So here we're changing the frequency of precession about the Z direction as a function of Y, okay? Remember, we're not applying the field in the Y direction, we're changing the amount of B field that the spins are experiencing as a function of their position in the Y direction, okay? All right, so what we're going to do now is actually look at some specific cases. We already talked about this slice selection. So if we have this GZ on when we apply our RF, we know we're exciting a particular slice within the anatomy. And so now let's just pretend that after that happens, so we know that we've tipped in this case we're doing a 90-degree pulse, so we're tipping all of the magnetization in that particular slice of the brain into the transverse plane. Okay, and then immediately after that, we're applying a gradient along the X direction. And in this case, it's a negative X gradient. So if you think back to our diagram, what that means is that these protons are going to be precessing slightly faster than these protons, okay? And so now I want to put you into the frame of reference of the actual isochromats. So we're going a step further and actually looking at the magnetization, not just the actual individual spins, okay? And for this particular demonstration, we're ignoring the effects of T1 and T2 decay, okay? So if they're precessing slower over here, that means that you can clearly see that this particular isochromat is precessing much slower. This one's precessing a little bit faster, and then this one is precessing at the absolute fastest, okay? Now, if we wanted to look at what it looked like with relaxation, it would look something like this. So we would have a decay in the transverse plane and a regrowth along the Z direction, but that's not very interesting for our purposes. So for now, we're going to ignore that relaxation, okay? All right, so if we apply this X gradient with a specific amplitude for a specific duration, for a certain amount of time, it's going to look something like this, okay? So we applied it for some length of time, and so in this particular case, these spins look like they're minus 90 from our isocenter, and these look like they're plus 90. And the reason this is minus 90 and plus 90 is because clockwise is negative, counterclockwise is positive, okay? And so if we apply it, so if we assume that, so this is applying it for some duration tau. If we apply the same gradient for some duration 2 tau, same amplitude, then we know that at the end of that duration, they're going to be that much further apart. So now they're minus 80 and plus 80, okay? And so this is what it looks like in the stationary frame of reference, okay? And so what I want to show you now is what it looks like in the frame of reference at the very center of the magnet, okay? So like this minus 80 and plus 80 is relative to this guy here right in the middle, okay? So this is our frame of reference on the merry-go-round, okay? Or and so what it looks like when we're actually on the merry-go-round is this. So we apply some negative gradient along the X direction for some amplitude for some duration tau, and we get the exact same behavior. So we get minus 90 and plus 90 relative to this guy. And then if we apply it for 2 tau, then we get something that looks like this. Okay, so we've got minus 180 over here, plus 180 over here, and I just want to point out that we're actually dealing with the rotating frame of reference at the center of the magnet. Okay? Does that make sense?